Last time we were talking about how to calculate the power dissipated at any location at any time. So now let's use that and examine the trade-offs associated with two different matching strategies. So we're gonna, for this segment, we're gonna start with an unmatched situation where everything's gonna look really bad. And then later on, we're gonna look at two matching strategies. One is a series match on the generator side, and the other is a parallel match on the load side. So just start out with we'll start out by looking at the basic unmatched situation. We have our generator and with its source impedance, which we will keep the same. Then off this goes into our transmission line. And we were very good in using a standard 50 ohm transmission line. But then we arrive at the load. And in this case, the load isn't very cooperative. So the load in this case is 2000 ohms. So quite different from 50 ohms. And then also on the generator side, we're going to have a 5 ohm load at the impedance at the source. So let's just start by drawing a balance diagram for in the interest of time, we'll just take a look at a few bounces. We'll calculate the key parameters nonetheless and see what ends up happening. So let's first of all, we look at what voltage goes in. So to do that, you take the voltage generator and you do a voltage divider between the transmission line characteristic impedance and the generator impedance. And remember, because this is a transmission line, you don't see what's going on the load side yet. So we have our generator voltage times Z naught over ZG plus Z naught, which is going to be equal to let's see, actually I forgot to declare, let's just say this is a 5 volt source. So VG is 5 volts, and let's just say VG is 5 volts times 50 for 50 plus 5. So in this case, the small load at the generator side works out pretty well because most of the voltage drop actually goes across the transmission line, so most of the wave goes in. And then the bad news starts happening when we're trying to do the reflection off the load. So we have new minus old over new plus old, which is going to be equal to our 2000 minus 50 over 2000 plus 50, and that's going to work out to be 0.951. And then on the generator side, you're going to have 5 minus 50, so ZG minus Z naught, new minus old, new plus old, and it's going to work out to be minus 0.818. So if we go back to our little picture here, over here on the load side we have 0.951. On the generator side we have minus 0.818. And the wave, the bounce diagram, we'll just look at a few bounces. But if you work through the numbers, you're going to find that, so initially we have 4.545 volts going in, and that's all well and good. And then, but when it bounces off here, the reflection coefficient is 0.95. So you actually have a pretty big reflection, 4.324. And then when you reflect off of the generator here, you also have a really strong reflection. So this works out to be minus 3.538. So that's multiplying 4.34 by this reflection coefficient. You're going to get this negative value. So what you see is that the voltage over here is going to be 0. This is going to be 4.5, and then it's going to go up to 8, and it's going to go back down to like 4, 5, 6-ish, and it's going to have a lot of reflections. It's going to take a very long time for it to reach steady state. So the bottom line is that it's going to be a very slow decay to the steady state. So this is the worst case. This is not what we want. So let's start looking at matching strategies. So first thing we're going to do, we're going to introduce the concept of series matching. So let's see, what do we mean by that? Well, that means it's what it sounds like. We're going to add something in series. This is something that we'll do on the generator side. So this I'll call SM for series match. And in this case, we want it so that it matches, that these two together match the transmission line. So if we want the overall series impedance here to match the transmission line, we want this to be 50 ohms. So to have this in series, you would want 45 ohms. If you set this to be 45 ohms, then the two added together is 50. And so now when you exit, your new minus old is going to be 50 minus 50, which is going to be 0. So let's go ahead and update these numbers and see what happens. So first of all, your input is going to, well, let's deal with this later, but let's just get to the exciting part about fixing things, because fixing things always feels good. So we didn't change anything on the load end, so the reflection coefficient over on the load end is still bad. But on the generator side, now if we look at what's new and what's old, at the output going out to the left, you're going to have 5 plus 45, that's going to be new, minus old, which is Z naught, which is 50, and then new plus old, so 5 plus 45 plus 50, which is going to be 0. So what that means is that you're going to have some kind of reflection off of the load end, and then it's going to come to the generator end, and then game over. And then the generator side is perfectly matched, and so that's basically the end, and then it reaches steady state. So what's the problem, right? This all sounds great. Well, the problem is when we start calculating this Vn. Because if you take a look at what happens, let's just draw the equivalent circuit. So you have your Vg, and then at t equals 0, what it sees is it's going to see your Zg, and it's going to see your Z series match, and it's going to see your Z naught. And so the voltage divider in this case, this is your Vn. Your voltage divider is now going to be Vg times Z naught over Z naught over Zg plus Z serial match plus Z naught, which is going to be 50 over 100, because this is 50 and that's 50, times your 5-volt input. And so one of the biggest issues is that you end up only having 2.5 volts going in here. And then most of it gets reflected back. So you get a large chunk being reflected back, 2.378, and then there's no reflections off here because right now one of the main change we made is that gamma g is now equal to 0. So you get a reflection off there, and then it comes back. And it's not as bad as it sounds, because remember, the voltage at the load over here is actually the sum of these two. So if you're looking at the voltage at the load, it's going to be 0, and then over here you have these two added together. So VL is actually going to be equal to around 4.878 going forward. So you still get most of the power across. So in that case, So on the surface, this seems like a really good solution. And when you're just looking at this, it doesn't really look like there's a trade-off. The trade-off largely comes from when you're actually doing it in real life. One of the problems that often occur is that your ZG isn't always constant. And so you can't always have a situation where you can have a perfectly good match for all possible VG values. And so even though it works great in this situation where there's only one value, it doesn't really pan out, and we still have to think of other solutions. So in that case, let's look at maybe we can do something on the load end and just take out the reflection there. Now you could do a series match, but then one of the issues that occurs there is kind of what you see here. You get this voltage divider, and so you get a much lower voltage at the load. And usually what you want is you want the load voltage to be somewhat close to your generator voltage, because that's often the voltage level that you're working with. And so what you would end up doing is you would try to do something in parallel so that you can have the same voltage. So let's just look at the parallel match situation. So we're going to do parallel match with this 5-volt source. Now we don't mess with the generator. What we're going to end up doing is adding another resistor here. So I'll just call this ZPM for parallel match. And then let's take a look and see what happens. So for starters, what do we want that value to be? That's going to take a little bit more finagling compared to series matching, so let's just actually calculate that out. So what we want is to have the two parallel values, CPM parallel C load, you want the two parallel together to be equal to Z naught so that you get a match. And so if you write out the parallel resistor equation, you can then solve for what ZPM needs to be. So if you move some stuff around to do a parallel match, you need it to be equal to Z naught CL over CL minus C naught. So this is how you find the value that you put in there for there to be a match. And in our case, using our numbers, that would be 50 times 2000 all over 2000 minus 50, which is going to be 51.3 ohms. And so when you do that, gamma L is going to be equal to C parallel match and parallel with CL minus 50, this being Z naught. I'll just be clear and write Z naught here. And this is ZPM parallel Z naught ZL plus Z naught. And we know that's going to be 0 because we chose the value such that these two values would be equal. And then gamma G remains the same. So it was 0.818 earlier. So let's update our little picture here. So now gamma G is still minus 0.818, but that doesn't matter because gamma L is now 0. And so let's just start up. So that means that we'll have to update these values, but what we expect to see happen is that once you have the voltage that goes in, it hits the load, and because it's perfectly matched, there's no reflection, and then everybody can go home happy. So let's just calculate the value of the voltage going in really quickly. So Vn is going to be the same as last time because it's the unmatched situation. So if I peek back at my notes as to what it was then, voltage divider between this 5 ohm and 50 ohm here, you end up getting 4.545. So you have 4.545 going on here, and then you're done. And then it gets there, there's no reflection, and you're done. But where is the drawback for this? Well, if you look at the power dissipated in the parallel match resistor, the voltage across here, it's already in steady state, and the voltage across there is going to be 4.545, right? It's basically VL, which is equal to Vn, because we just did that match. And so if we square that, divided by 51.3, which is the resistor here, so V squared over R, you're going to get 0.403 watts, or 400 milliwatts. In comparison, the generator side series match, I have the math in my notes, but I didn't do it just now. But in comparison, that one has 0.26 milliwatts for the series match. And so if you compare the two, you're dissipating a lot of power into this resistor. And so that's probably the biggest drawback of this parallel match situation. But if you're able to afford it, it solves the issue where in situations where the source impedance might change a lot.